This is Isaac Physics question D5.8. Just pause the video now, take a second to read the question. So this is my diagram of what I think this instrument would roughly look like. You've got this tube here, and it's 1 meter long, and at the bottom of the tube there is some water. You have to find the depth of water in the tube if the fundamental frequency is heard at 125 Hz. Now, this is a tube that has got one end closed. This is closed, it's not open, and this end is open. What that means is when we have a standing wave in here, because this end is closed, it will be a node. The air particles can't move through that closed end. So because there's no movement there, means it must be a node on a standing wave. Because this end is open, the particles are moving at that point there, and they'll have a maximum amplitude there. That will be the antinode. So for a standing wave where I've got one node and one antinode, it's the fundamental frequency. The wave will look something like this. So drawing that again, so it's a bit more clear over here on the right-hand side, it will be a wave that looks something like that, where it's just, that would be like a small section of a bigger wave that would do something like that. Because this is just a tube that's got one closed end and one open end, it means this must be a node, this must be an antinode, and because it's the fundamental frequency, it's the lowest frequency that you can have in there, so it would look like that. Given that they've told us the frequency is 125 Hz, we can now use the wave equation and work out the wavelength, because it will be c over f. For this wave, the wave speed is 330, because this isn't a light wave, this is just a sound wave, 330 over f, which is 125, and that gives us a wavelength of 2.64 meters. If you look at this wave I've drawn here, this is one wavelength, but the wave that we've got inside our instrument, inside this bit of tube here, is just this section here, because it's the fundamental frequency. We've got the node and the antinode. So this is just a quarter of the wavelength. So that must mean that this length here, which is the same as this length here, is a quarter of the wavelength. So that means that length of that section there is 2.64 over 4, which is 0.66 meters. So you can see here, I know that the length of that bit, the length of the wave was 0.66 meters, the length of that bit of wave. That is the length there then, so that section there must be 0.66 meters. But the question's asked us to give the depth of water in the tube, so it's looking for this length here. So how are we going to do that? Well, to do that, we're simply going to do 1 minus 0.66, because 1 is the length of the whole tube, and 0.66 is the length of the air section, so the length of the water bit will be 0.34 meters. But there you go, that's how we do part A of that very difficult question. This is again a very difficult question. This is part B of that question, so just pause the video, take a second to read it. So I've drawn over here what we had in part A, where for the fundamental frequency, the wave would look like that. But now for this part, it's saying the lowest frequency above the fundamental frequency. So this is what it will look like, the tube over here. What will the wave look like? Well, considering again that I've got a node at the bottom, and this must be an antinode, the wave will look like this. The next one above the fundamental must look like that. That wave has still got a node on the bottom, which I know must be there because that is a fixed end. It's a closed end, it's a fixed point. And up here, because it's an open end, it must be an antinode. I'm just going to leave it as AN. So this time, the bit of wave that is in there is this section of a full wavelength. Before it was just a quarter of it, now it's 3/4. This wave here is 3/4 of a wavelength. So if the length of that bit of air in the tube was 0.66 meters, which is what we found before, and I also know that it is now 3/4 of a wavelength, then I can work out what one wavelength is. One wavelength is going to be 0.66 over 0.75. And that gives me the wavelength as being 0.88 meters. The tricky final bit of this question is recognizing that 8 centimeters above the surface of the water is going to be between the first node and the first antinode. It's only 8 centimeters up there, whereas this whole thing is 0.66. So 8 centimeters is going to be a tiny little bit up. The question asks for what height will the particle's displacement be out of phase with that? So where will there be a particle that is out of phase with this point here and has the same amplitude as it? Well, to be out of phase with it, it won't be on this part of the wave. All these bits are in phase with each other. The particle that will be out of phase with this bit and have the same amplitude will be this point over here. It will be 8 centimeters up from the next node. The particle we are told about is 8 centimeters above the surface, so it's 8 centimeters above the first node. The other particle we're looking for will be 8 centimeters above the second node. This is a node here. We're looking for 8 centimeters above that. This is half of a wavelength, so this length here will be 0.44 meters. The whole wavelength is 0.88, so this half of a wavelength here will be 0.44, which means that the height of the particle we're looking for will be 0.44 plus 8 centimeters. It will be there. Plus 8 centimeters, and that will give us 0.52 meters as being the height of the particle above the surface of the water.